All right, so as promised, we're going to go back to part 6 and pick up this concept of allotropes. Don't have a whole lot to say about it. Other than kind of the reason allotropes came up was because of this. So I'm going to focus on the allotropes of carbon. I think I mentioned this before, but it's important that we've talked about these are enthalpies of reactions, right? These are enthalpies of reactions associated with these specific reactions. That means these specific coefficients, and also means this stuff in these particular physical phases, and in the case of carbon, not just a solid, but in the allotropic form of a graphite. So it's just like really kind of nitpicky. But if we pick on carbon, actually carbon has an assortment of allotropes. And if you're familiar with what makes up a diamond, you know, carbon atoms make up a diamond. So, and carbon atoms also are shown here in the form of graphite, which is kind of like lead. So carbon atoms are carbon atoms, right? You know, they will react differently and give you different heats of reactions. So this is what a diamond would look like. This is what graphite would look like, kind of sheets. Those little knobs are carbon atoms stuck together. So we have a third allotrope of carbon called the buckyball. And historically, I think I got this right, it was first actually found on material that came from outer space. On, yep, a meteorite. Yep. So, what are buckyballs? They're just, and the fact that it was first found in naturally occurring in a space rock, I would imagine it at low temperatures and low pressures, carbon can gather in that form. So, extraterrestrial and all that. Okay, another buckyball. And then carbon is also can be make these nanotubes. You might have heard of these. These are very strong carbon fibers. Carbon fibers. Mm-hmm.
They're very light.
Very light. Yes. All right. So the whole point there is when you're dealing, you have to be careful when it gives you a balanced equation. What is the physical form, or which allotropic form of it of the elements are there? Actually, that kind of leads us into a good place, because we're going to also have to be picky when we talk about this next topic of standard molar enthalpies of formation. I just love that, standard molar enthalpies of formation. I don't memorize a lot of things, but in that word, standard molar enthalpy of formation, it says what it is. It's in standard state, it's the formation of 1 mole, and it's the enthalpy associated with it. Standard molar enthalpy of formation. So this is this, anytime you see a delta H sub F, the F means formation, and you also said delta H naught, that means the standard conditions. So delta H naught sub F means the standard molar enthalpy of formation of something. So let's see if I have my little pen here. In that definition are some key things. Maybe not. I guess so. I was just going to underline the 1 mole formation from elements in their standard states. Now, I wish I could find my pen. Standard states, don't let that form fool you. What are the 3 states of matter?
Gas, solid.
Thank you. Gas, liquid, solid. Plasma, 4th state of matter, right?
Yeah.
So standard, what are the standard conditions? Thermodynamic. This is the knot. Remember I said that actually sometimes that makes it to my test? Wait a minute, I didn't say that, but what's the standard temperature for thermodynamic problems? I'm going to put you on the spot because you're on your phone and you're in the very front row. Okay, so what is the standard temperature for thermodynamic? I've got a test on Thursday.
25.
Yes, sir. 25 Celsius.
I was only 75 off.
Standard pressure.
1 bar.
1 bar. Thank you. Yep. Okay, so here's my thing. By the way, 1 bar, that's about 760 millimeters of mercury. It's about 1 atmosphere. My point is, that is here now. That is in this room. I don't know, 25 is a little bit warm, but. So, for instance, iron. What, if you think of iron, what is it going to be, a solid, liquid, or gas right now? Solid, exactly. So actually, Fe sub S, that's in its solid state. Okay, oxygen. First off, oxygen, tell me what's wrong with this. It's diatomic. In this room right now, is oxygen solid, liquid, or gas? It's a gas, exactly. So that's what it means by we are making a compound, or we're going to form 1 mole of substance from the elements in their standard state and standard conditions. Okay, so keep that in mind. Standard state, this is what I was just talking about. You guys told me iron will be solid, I agree. You guys told me oxygen will be a gas, I agree. Okay, so in standard conditions, you guys told me 25 Celsius, finally, for thermodynamic problems, and 1 bar for thermodynamics problems, which is great. So here's one to keep in mind, to put in the back of your mind. So delta H sub F naught, so the standard molar enthalpy of formation of anything in its, any element in its standard state is 0. So that could come in handy. You're going to see that pop up here in a minute. These actually, I just took I copied and pasted a slide from part 6 here. You might recognize these as our puzzle pieces. These, and if I had my pen, I would draw on it, but these actually are equations representing standard molar enthalpies of formations. Check this out. The product side, what's it forming? C6H6. It's liquid state. I buy that. Benzene, liquid, and room temperature, room pressures. Notice it's making it from what? Carbon and hydrogen. And by the way, this is where I kind of got nitpicky about the allotropic form of carbon graphite. So graphite is carbon's standard state, solid graphite, at 25 Celsius and 1 bar pressure. And this one actually is also a standard molar enthalpy of formation of, what's on the product side? CO2, from the elements in their standard states, at standard conditions. This also is the formation of water, okay? So these actually, again, if I had my pen, I would do this. I could take all those delta H's 1, 2, and 3, and I could replace them with delta H sub F's, delta H naught sub F's, because they are standard molar enthalpy of formation of C6H6, CO2, H2O, standard molar enthalpy of formation. Okay, so on this next slide, I'm going to show you some equations, and you're going to see some enthalpies, some delta H's at the end there for the reaction. And as written, the question posed to you, do they represent the standard molar enthalpy of formation? If they represent the standard molar enthalpy of formation, then their delta H's are the delta H sub F's. They're special delta H's, okay? So for instance, I'll let you look at it. Now, there's like at least 3 criteria. 1, does it form 1 mole of product? Yeah. Okay. 2, does it form it from elements? Because if it forms it from compounds, that's off. It does not represent the standard molar enthalpy of formation. Yep, those are elements. And are these elements in their standard state graphite? Yes. So yeah, I would say yes, that one does represent the standard molar enthalpy of formation. So if I had a pen, I would put a little F subscript right here. Like under, see where the H is? I put an F there. Because it is, yeah. How about this one? See, do you see anything that would make it not represent the standard molar enthalpy of formation? Anybody see anything that would make it not? No. Well, I think it is the standard molar enthalpy of formation of PbCl4. So yes, I put a little F there. I'm digging it. Okay, how about this one?
Yes.
What's wrong with it?
PCl.
Yep. This is what's wrong. You could circle this if you wanted to. That's what's wrong with this one, because it has to be made from elements in their standard state. Yep. And this is an element, it's a compound. Yep, so you can't put an F subscript there. How about this one?
Yeah, because it made 2 moles.
Can't fool you, Maddie. Yep, I agree. She's gonna circle this one right here because it has to be the creation of 1 mole, and this is 2 moles.
So none of those seem to be.
These
The first
two,
two.
yeah, these 2 are not, but the first
The
2
first
are.
one,
Mhm,
yeah.
The first 2,
Yes.
the first 2. So this last one, I agree. So how could we take this, the heat of this reaction, the enthalpy of this reaction, and how could we get the standard molar enthalpy of formation? Divided by 2. Exactly. We could rewrite this thing, go through by a factor of 2. Exactly. Perfect. So here are some values that kind of, looking at tables sometimes, they make my head spin. The way this table works is you would divide it right here. So we have substance, enthalpy of formation, substance, enthalpy of formation. Some of the things that I think are interesting, so would you say, are all of them exothermic? Are there any endothermic? There's a few endothermic. Most of them are exo, but there's a few endo. I think that's pretty cool. And then this is, I just have a few screenshots of what you'd find in the OpenStax book. This is Appendix G. Okay. So it's organized by element, and I don't see the word calcium up here, but it should be. I would have calcium, and these are all calcium-containing compounds. Now, we are just dealing right now with this first one, this first column. The other 2 columns actually we cover in Gen Chem 2, other thermodynamic properties. So here's calcium, carbon, and notice that, why is this 0? Because it's a standard state, exactly. And we said that if you're going to form an element, or the standard molar enthalpy of formation of an element in its standard state is 0. Like if you were to form it from itself. Yeah, I was just thinking, it's just, to me, it would just look like, I hadn't really thought about that. It'd be like, carbon, solid as graphite goes to form, carbon solid as graphite. But I can see, and you can see here, that if we are going to form another allotropic form, like diamond, so this delta H is 0. But this one is not 0, is it? Where it's, for instance, we could take the diamond. Solid is a diamond. And in that case, we would form it from carbon, solid as its graphite.
Can you make diamonds out of graphite?
With a lot of pressure. I don't know how that works.
Well, yeah, we're under financial pressure because we're poor.
Physical pressure. Chromium, cobalt, so we kind of get the idea. So it's interesting to see a few zeros there, and that's just because in its standard state, the standard molar enthalpy of formation is 0. Okay, so let's work a problem. Let's say you're dealing with methanol. It has 2 carbons, 6 hydrogens, and 1 oxygen. And we have to write the equation for the standard molar enthalpy of formation. Well, the way I would start is, I need to consider carbon, hydrogen, and oxygen. And I would jot down what I'm going to be dealing with as reactants. So carbon, we said we're going to go with solid as graphite. Hydrogen, what is that going to look like?
H2.
It is going to look like H2, exactly. Bless you. H2 specifically in its gaseous state. And what about oxygen?
O2.
Yep, O2 in its gaseous state, perfect. So those are going to be our reactants. And we need to make the equation balanced. And if it's going to be a standard molar enthalpy of formation, we can only form 1 mole of C2H5OH. So it kind of looks like this. On the product side, I'm going to put what I'm trying to form, C2H5OH. And then, and oh, by the way, you may not would have known this, but well, it has an L up there, so it's in liquid state. So then I would write down my 3 reactants. Carbon, hydrogen, oxygen. Specifically, carbon as a solid, the allotrope graphite, hydrogen in its gaseous state, and oxygen in its gaseous state. So we got to balance it. What coefficient will go in front of the 2? Or, you know what I mean? What will go in front of the carbon? 2, right? We need 2 carbons. What coefficient will go in front of the H2? 3. Just 3, yeah. 3 will give me 6. 6, I need 6, yep. 3. Very good. So, yep, so what will go in front of O2? 1 over 2, 1/2. Yep. So we have just created an equation representing the standard molar enthalpy of formation of C2H5OH. Yay for us. Okay, so hold that part.
Go back just.
Okay.
So we need 1/2 of O2 because it's O2.
Right.
And we just need the O.
Right. Yep. If you double check, we need 1/2 the O2 because it's O2 and we just need 1 oxygen. Yeah. Okay. So, I think if we scroll back a few slides, you're going to find methanol listed somewhere as a liquid. You would come up with its, the heat of the reaction is, well, I don't know, I guess I'm going backwards on this. You would find out the standard molar enthalpy of formation is exothermic, negative 277.6 kilojoules of mole, kilojoules for every mole of C2H5OH you created. And do you see where I can go ahead and say for this reaction, the enthalpy of that reaction is also negative 277.6 kilojoules of energy, so. So they're interchangeable if it meets these special criteria we've been talking about. Okay. So here's one for you. Well, a few things. When we talk about deltas, changes in, it's always final minus initial, right? So also is our first time, I think, to apply this, maybe not. We ran into the summation before. Summation, we ran into it before when we calculated the average atomic weights. So this means to sum. Oops, okay. So if we want to knock out the change in enthalpy for any reaction, okay, we can actually do that by summing up. It's always final minus initial. So we go with the products first. So what we're going to see here in a minute is we're going to see, oh, I'll just do it this way. So if we have R1, R2, we have 3 reactants, goes to form 3 products. 2 products, 3 products. Okay. What we know is we can look up the enthalpies of formation of all of these. We can have enthalpy formation of that, 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 formation of that. So what we can do then is basically sum up the enthalpies of formation of the products. That's going to go here. And from that, we are going to subtract the summation of the reactants. And that is going to go right there. I'll show you how it works. Okay. There's one more twist. We need to go ahead for each time we need to take their standard molar enthalpies of formation times their stoichiometric coefficient. So bless you. Let's do an example. Let's do the combustion of benzene. So we're taking C6H6, we're reacting with oxygen. This is a balanced equation. We're going to give us carbon dioxide and water. So to work these problems, I see two problems. People don't stay organized with them, and people, myself included, lose the sign sometimes. So you're gonna see on the next few slides, we're gonna take 6 times the standard molar enthalpy of carbon dioxide, which is this one, negative 393.5, plus 3 times the standard molar enthalpy of formation of water, negative 241.8. And actually we're gonna add them together, and that's gonna be this guy right here. Then we're going to take 1 times the standard molar enthalpy of formation of C6H6 plus 15 halves times the standard molar enthalpy of formation of oxygen, which of course is 0. And that's going to be this guy right here. And then we're going to do one last subtraction. That's how that looks. So here we go. Focusing on the product side first. The coefficient in front of the CO2 is 6. So we have 6 moles of CO2. From a table, or the table, we know the standard molar enthalpy of formation of CO2 is negative 393.5 kilojoules per mole of CO2. Then we have to focus on our water. The water term looks like this. The coefficient in front of the H2O is 3, so we have 3 moles of H2O. From a table, we know that its standard molar enthalpy of formation, see, it just has a great phrase, standard molar enthalpy of formation, is negative 241.8 kilojoules per mole of H2O. And the way I do this then is go ahead and tap that in my calculator. Sometimes students are tempted just to go ahead and do it all at once, but I don't think that's a good idea. So tapping it in my calculator, I come up with negative 3,000, negative 3086.4. Negative 3,086.4 kilojoules of energy. So we found this guy. Okay. Then I draw a squiggly mark or label it on my work. Now I'm going to go for the summation of the reactants. So it looks like this. We have the 1 mole of C6H6 times its standard molar enthalpy of formation, and sometimes I'll put a plus there, so I know it's endothermic, but times positive 49.0 kilojoules of energy per mole of C6H6. And then it's easy to blow off this term, but you probably shouldn't, because we have another reactant. That was the 15 halves moles of O2. It just so happens that its standard molar enthalpy of formation, since it's in its gaseous state, is 0. So 0 kilojoules of energy per mole of O2. I can do the math there. Okay, so we go ahead and finish this out, and I come up with plus 49.0 kilojoules of energy. So once I have this term, the summation, and this term, the summation, then I'm ready to do my subtraction. And it looks like this. Oh, do you need it back? Okay. What throws me off, is if this is negative, because then I have to remember that I'm going to subtract a negative. But we do a lot of that, I guess. Okay, there we go. So applying this formula then, we get the summation of our products, which was that negative 3086.4 kilojoules, negative 3086.4 kilojoules of energy, summation of our products. From that, we subtract the summation of our reactants, which is 49.0 kilojoules. And we rounding's a tricky thing in these problems, but we're subtracting, so we'll go decimals. So we get a negative 3,135.4 kilojoules. Is it a big spider?
That's
Bless you. This one?
almost done.
The older I get, I actually pick up spider now. I can, but. Okay.
There's nothing to lose anymore.
No.
That's it.
You got this one too?
Yeah, I got. Oh, I got the second. Sorry.
So what we found out after we sent everything is the specific heat.
We found out the heat of that reaction, the combustion of benzene, the C6H6 plus the 15 amps O2. We found out the heat of that. This is the react for the overall that reaction. Yeah, we looked at the pieces and came up with for that reaction. The enthalpy change for that reaction. So that's about how far I wanted to get today, guys. So this homework is early. This homework is due Monday. I was at my desk working these, and these are fun. So it kind of combines Hess's law and standard law and empathy information.
Yeah.
Okay. All right. This is it.
I don't know that one off the top of my head.
No.